Hello, everyone. This is Team 18, also known as Team 747, and we're here with our team project Deliverable 3. Our project is drones for the enhancement of agriculture development, also known as DEAD. And I am Jarett Cardiff, and I'm here with my teammates.
Michael Pettiford.
And Brandon Burpo. Our swarm problem statement is that agricultural upkeeping is backbreaking and difficult. Farmers face challenges in effectively monitoring crop health, detecting pests or diseases, and optimizing irrigation needs, which leads to suboptimal decision-making and resource allocation. This project will see the improvement of the aforementioned challenges through the implementation of a drone swarm. The context or application is in agriculture, there's a need for increased crop yield per acre. Existing equipment tests soil, water, and applies spray and fertilizer, but the process is labor-intensive and lacks efficiency. Our swarm aims to enhance crop yield by optimizing soil nutrients via our soil tester and our fetcher, and providing adequate water, pesticide spraying, and adequate or additional nutrients like zinc or nitrogen via the DEAD spreader.
For our agricultural robots or swarm, our direct customers will be farmers. That's going to be our main focus. Our indirect customers will be botanists, arborists, environmentalists, and investors.
So now we're going to go over the introduction to our design requirements. So the design shall be able to maintain a 50-acre plot. More pods of drones can be used. The swarm of drones should be equipped with precise and targeted spraying mechanisms for the controlled application of fertilizers or pesticides, reducing chemical usage and minimizing environmental impact, while utilizing a 15-gallon storage tank to hold those fertilizers and pesticides. The design shall incorporate advanced image processing and machine learning algorithms to analyze the collected data and provide actionable insights regarding crop health, pest or disease presence, and irrigation requirements. The drone should be capable of capturing and transmitting real-time data to farmers, allowing them to make informed decisions promptly and optimize crop yields effectively. The design shall optimize energy efficiency to ensure extended flight time and reduce the need for frequent recharging or battery replacement if it comes to it. Design shall be able to be tracked via GPS, while also having the ability to be controlled from a user interface.
For our types of individual robots, you have the DEAD spreader by myself, a robot that can spread a liquid of your choosing onto farmland.
For our second robot, we have the DEAD soil tester, and this robot will drop probes for soil analysis.
For our final robot, we have the DEAD fetcher. This robot will retrieve probes dropped by the DEAD soil tester.
Good afternoon. My name is Brandon Burpo, and today I will be presenting you the DEAD spreader. The red, green, and black LEDs you see on the wings of the robot serve a dual purpose. One of the purposes is providing blinking lights similar to most aircraft, and the second purpose is to identify where the motion sensors will be located on the wings so as to avoid collisions. It is important to note that while the measurements are in millimeters and in centimeters, it is designed to be scalable so long as you keep the proportions relative to each other. This is simply a miniature design to showcase the robot's functionality. So as long as you keep every component of the robot relative to one another and scale it to a larger size, you'll be able to get a larger robot when you need to build a larger version of this. This is the rear view of the DEAD spreader. I'd like to point out that the cutout portions of the robot's wings and tail fins are the locations where the servo motors are going to be placed, allowing for the automated steering of the robot when something gets too close. So you can see the two cutout portions on the wings and the two cutout portions on the tail fins. That is where the servo motors are going to be located. This is the front view of the DEAD spreader. Please note that refer to the previous slides for dimensions. This is simply to show another view of the mechanical design and show the different components that are listed throughout the robot. As you can see, the propeller up front is going to be controlled by the motor that you will see later in the design slides. The Arduino boards will be located inside the wings and the main body of the robot so that they provide protection to the electrical components from the weather and any physical damage the robot may suffer. So these Arduino boards are going to be located just inside the flaps that you see on the wings and then within the main cylindrical body of the robot. This is the underneath view of the DEAD spreader. This is a view from below of the robot in order to showcase the tank that would be holding the liquid of water or pesticide. The spout below this tank is going to be controlled with a button or switch that the main controller is going to be able to activate with a single command. This is the circuit design. Here you see the overall layout of the circuit design for the entirety of the robot. It is important to note that these electrical components will be located inside the robot so as to avoid any physical damage or damage from the elements. I like to point out the 3 distance sensors on the 2 that are on the edges of both wings and the 1 distance sensor in the front. That is to avoid collisions of anything coming within 12 inches or 1 foot of the robot from the left, the right, and the front. There are 3 Arduino boards, one located on each wing and one in the main body. There is a motor up front, 4 servo motors. There is 2 servo motors, one on each, 2 main servo motors, one on each wing, and 2 mini servo motors that are in the tail. It's controlled by one 9-volt battery, and there is a breadboard with a L293D chip, as well as a button to control the tank below. Here you see the Arduino code for the main body. I'm not going to get too in depth on it, but it sets up the motor pins and the pins for the distance sensor and everything like that in order to control the individual components listed within the circuit. Here is the code for the left wing. It sets up the motor pins for the servo and then attaches the servo to the motor pins, as well as sets up the distance sensor on the left side of the wing. This is the same as the left wing, however, it's on the right side, so it's going to set up the distance sensor on the right, the servo motor on the right, and the motor pins for that servo motor. Here's the flowchart for the main body. This is the logic or flow of commands that the robot will receive in order to execute the running of the motor up front, the turning of the tail fin servo motors, the dumping of the water or pesticide that it will be carrying, and finally returning to base after completion of its flight or to restock the tank and continue spraying. So it's going to start, it's going to set up the pins for the motors and everything. It's going to attach the servo motors, and then it's going to begin serial communication. It's going to ask if the button's pressed. If it is, it would have received a 1 command, which would result in the number 49 and then release the payload. It is then going to ask if there is any object in front of the aircraft that is less than or equal to 12 inches in distance, or 1 foot. If there is, it's going to relay a command back to the tail fins in order to turn away. And then once there is nothing within 12 inches from the front of the aircraft, it's going to continue flying straight. And then it's going to ask if the payload is empty. If it is empty, it's going to receive a 0 command or a 48 and return to base. If the payload is not empty, it's going to go back up to receive the 1 command, release the payload, and then continue back through the flowchart process. Here's the flowchart for the left wing. This is very similar to the main body, but with less components because there's no button and there's no motor. There's just a servo motor. So this is the string of commands for the left wing of the robot in order to automatically turn in the event of an object coming too close in proximity to the left side of the robot, such as a bird or another aircraft, in order to avoid collision. So similarly, it's going to start, it's going to set up the motor pins, it's going to set up the distance sensor, it's going to set up or attach the servo to those motor pins, begin serial communication, and then this is just going to ask if there's anything less than or equal to 12 inches from the left side of the aircraft. If there is, it's going to turn away until there no longer is anything within 12 inches of the left side of the aircraft. Once there isn't, it's going to continue flying straight, and then it will end. The right wing is basically a reflection of the left. However, everything is flipped to just mimic the right wing or the left wing, but on the right side. And now I will show you a demonstration of the Tinkercad circuitry. I already have it started. So the servo motors are going to kick up and then return back to normal. And then once you take the distance sensor and bring an object within 12 inches, you can see that the servo motor is going to turn in order to avoid collision. And that is the same for every single distance sensor. As you can see, these are turning down here in order to avoid collision from the front. And then this is turning to avoid collision from the left side. And if you bring it back outside of that 12 inches, then the servo motor will return to normal and continue flying straight. That is the same for all of the servo motors and distance sensors. So if you wanted to release the payload, you can simply send a 1 to the aircraft. It will show the number 49, which is going to then press the button. And once it presses the button, it will release the payload. If you send a 0 command to the main body, it will send a 48, resulting in a return to base. This has been a presentation on the dead spreader, and next I will be followed by Jarett to present his robot.
Hey everybody. Today I'm going to be going over the dead soil tester. First, I'm going to be going over the mechanical design overview by first going over the inputs of the robot, and then by going over the processes and outputs of the robot, along with some safety mechanisms that the robot has. First, for the inputs, battery level, the drone checks the battery level to ensure it has sufficient power for the flight. Pre-checks, the drone performs necessary checks before taking off, such as system diagnostics as well as sensor calibration. and as well as GPS and altitude sensors. The drone activates the GPS and altitude sensors to obtain precise positioning information. And lastly, we have a target soil location. The drone receives information about the designated soil sampling location. Now for our processes and outputs, we have fly to target soil location. For this, the drone navigates to a specified soil sampling location using its propulsion system and flight control algorithms. We also have the activate the soil sampling probes. These are probes on the drone, and the drone deploys the soil sampling probes to penetrate the soil at various depths, which will be gathering information. And leading that, we'll have gathering data and using soil sensors and probes. The drone collects data on the soil composition and fertility using pH meters, moisture sensors, and nutrient detectors integrated with the soil probes. And all this information is stored on board or transmitted. The collected soil data is either stored on board the drone for later analysis or transmitted in real time to the ground station for immediate evaluation. And lastly, we have a return to base station. After completing the soil sampling task, the drone returns to the base station using its navigation capabilities. And along with that, we have a perform landing and shutdown. The drone executes a controlled landing and shuts down its systems. A couple outputs for the robot. We have collected soil data. So the drone provides the collected data on the soil composition and fertility, which can be used for further analysis or decision making. Stored and transmitted data. The drone either stores the soil data on board for later retrieval or transmits it to the ground station for real-time monitoring and analysis, like we talked about. Another thing is a couple of safety mechanisms is in case of a fire. An input for the robot is fire detection with the light sensor, detects the presence of fire, and the process and output for that would be fire detected. The robot recognizes that a fire has been detected by the light sensor and activates a emergency response, which would engage a safety protocol. Now moving on to the soil tester, or the soil tester mechanical design dimensions. As you see here, it's the Tinkercad write-up from different angles. Now here we have the soil tester circuit board, where it's connected to 3 servo motors, a DC motor for the propeller, a 3D distancing sensor for the entire drone, and a photoresistor for that light detection. And lastly, that's powered on the 9-volt battery. Here, this is the soil tester Arduino code that goes along with the circuit board for Tinkercad. And here is the flowchart. Just going over the flowchart briefly, is it would start, check battery level input, perform pre-flight checks input, activate GPS and altitude sensors input, and fly to target location input, activate soil sampling probes input, and then gather data and store data or transmit data, and then return to base station and perform landing shutdown. And then a couple excesses, the fire detection with emergency response. And yeah, that'll be the end for the flowchart. Now I'll move into the demonstration of the dead soil tester circuit board on Tinkercad. So here we have our dead tester circuit board on Tinkercad. This here is our following code for the circuit board, which here we have the pins for the sensors, pins for the motors, thresholds for the sensor readings, initialize the servos, set the motors. And here's when we run the simulation. As you can see, everything starts to work very nicely there.
Hello, everyone. Like I said earlier, my name is Michael Pettiford. I will be showing you guys the design, my design of the dead fetcher, which is going to be a rover-like robot that will retrieve the probes that are dropped by the dead soil tester. It's approximately 95 by 82 by 75 centimeters overall in dimension, with 4 DC motors powering each of the 4 wheels. There are 2 servo motors on the undercarriage to open the bay doors. Those bay doors allow for the collector to drop in order for probe retrieval. There's 1 proximity sensor in the front and the rear for collision avoidance and avoiding obstacles. Here you can see the mechanical design from the top and bottom. Labeled, you can see the front proximity sensor, the rear proximity sensor, back DC motors, front DC motors, and the 2 bay door servo motors. These bay doors will swing open just like an aircraft's bay doors to retrieve the probes that are dropped. There's another slide showing the front and rear, and a slide showing the side. Here you can see the dead fetcher circuit design. We have the front proximity sensor, as noted earlier, the rear proximity sensor, the front left DC motor, front right DC motor, back left DC motor, and back right DC motor. Those DC motors are powered by 2 L293D chips, which are also powered by 2 9-volt batteries, each one supplying power to 2 motors. You can also see the bay door left servo motor and the bay door right servo motor, and everything's going to be attached to this Arduino right here, which is going to be doing all the computations and data inputs and reception of those inputs. In this slide, we have the dead fetcher logic flowchart. All processes have to start somewhere, and this one starts with a command from the central hub telling the robot to start. Once the robot starts, the Arduino will go through its setup. So firstly, it'll attach the left and right servo motors to pins 5 and 6. It'll set the left and right servo motors to 0 degrees, which is the bay doors being closed. It'll set pins 5, 6, 7, 8, 9, 10, 11, 13, and alpha 2 as outputs. Now those outputs include the DC motors, 4, with forward and reverse, and the proximity trigger pins. The inputs will be pins 12 and 1, and those are going to be the proximity sensors echo pins. After that, we'll begin serial communication, and after that, serial print the hub command and the front and back distances. The first question that's going to be asked is if the distance from the front or back proximity sensors is less than or equal to 20 inches. If yes, the robot will initiate an avoidance sequence, which is going to stop the robot, turn it right, and then stop it again. If the distance is not less than or equal to 20 inches, the robot will wait for a hub command for input. So at that point, the central hub is going to tell the robot whether to move forward, reverse, left, right, stop, retreat, and retrieve the probe as necessary. Here you can see each of the inputs is related to an alphanumeric number. So 1 will be forward, and that will power all forward motor pins. 2 is reverse, and that will power all reverse motor pins. Right is 3, and that will power the left forward motor pins and right reverse motor pins. And left is 4, and that will power the left reverse motor pins and right forward motor pins. We also have 0, which is going to be our stop command. That will cut power to all motor pins. And finally, we have our retrieval, command number 5, and that will initiate the retrieval process. So we'll stop for 2 seconds, right the servos 90 degrees, go forward for 5 seconds, stop for 2 seconds, then right the servos back to 0 degrees, closing the bay doors. Then reverse for 5 seconds, returning it to its original position. And then finally, it'll stop. If the job is complete, the distance sensors will be statused again, and then it'll go back to the command hub through all these inputs, whatever the command hub dictates it needs to go through to get back, and then the process will end. Here we have an overview of all the coding. And now let's move on to the demo. Here we'll have a brief demo of my robot. Start the simulation. Let's go through the code. Like I said earlier, if we press 1 in the serial monitor, the robot will start moving forward. 2 will make it go in reverse. 3 will make it turn right. 4 will make it turn left. 5 will make it do its retrieval process. Stop. So the bay doors will open. It'll move forward for 5 seconds. Stop again. Close the bay doors, and then reverse for 5 seconds. After which it will stop and receive input from the serial command again. We'll say 1, and then 0 will make it stop. If the distance at the front proximity sensor or rear proximity sensors go below 20 inches, the robot will initiate an avoidance maneuver. And once the distance goes above 20 inches, it will stop that maneuver. Here it is for the rear. That's the dead fetcher, guys. Thank you. So for our collective behavior, it's going to be an ongoing process, but it's going to start with the central hub initiating the soil tester. The hub both analyzes the data and dictates requirements for pesticides and fertilizers, while also activating the fetcher for probe retrieval at the same time. With the soil tester going out, the hub activates the spreader to spread water, fertilizer, and pesticides. And with the fetcher going out, the fetcher will then retrieve the probe, and then the process will start again from the soil tester initiating.
So in summary, some of the lessons learned that we came across during this project were the time management skills, the use of teamwork, the fair division of labor across all 3 members, and optimizing the design process.
Things we would do a little bit differently in the future. Definitely invest a little bit more time into learning the code as well as the circuitry. We would always focus on utilizing the Gantt charts more as timelines and sticking to them hardcore.
Sum everything up. This project aims to help farmers by implementing a drone swarm system that monitors crop health, identifies pests or diseases, and optimizes irrigation. Drones with specialized functionalities analyze data, provide insights, and enable real-time decision-making. The system covers around a 50-acre plot, uses accurate spraying mechanisms, and incorporates advanced data analysts in real-time data transmission, energy efficiency, and GPS tracking. Algorithms control the drone's task, allowing them to adjust flight paths, activate sensors, and relay information. This system enhances crop monitoring, reduces chemical usage, optimizes resources, and increases profitability. Collaboration with investors and agricultural researchers ensures cost effectiveness and compliance with industry standards, making farming practices more efficient and sustainable.